for feature generation. Okay, so we are at, let's say we want to compare if two strings are equal, right? Again, Python gives you big superpower, right? So you're able to create counter of S1 and counter of S2, and you can simply subtract them. See, that's the cool thing about counters, right? So counter is so powerful. Like if I'm writing a coding question, I'm like, because look, something writing this, you're solving this big problem, right? And just this part is a teeny tiny portion of the whole algorithm you're solving. And then comes right these 4-6 lines of code, like you're going to be beaten by time. Just tell the interviewer. So since you're using Python, we can use the counter, we can use counter from collections module. I'll explain that to you very soon. And then you can create this, and then there's a subtract you are there. Now, where are counter and default sticks from? When we use counter in default sticks, you have to import them. They're not like automatically, when you create a Python file, they're not automatically given to you. In LeetCode has imported all those things. So you can just do counter and default it and you go. But as an engineer, as a programmer, you need to know where they come from, right? They both come from the collections module. So collections. So you first have to do import collections. Please, these things are important. Don't just do LeetCode and go sit an interview and just be like, counter default. And the interview will be like, where is default sticks from? You'll be like, Python gives it to you. They're going to be like, sorry, they don't give it to you automatically, right? Like Python gives you import, so you have to do like import collections, right? That is where it comes from. You've seen imports in Python code before, right? Import simply means, hey, bring the guy in, right? So default, the full name is collections dot default dict, right? But then, you don't want to go through this. So I think you can just do from. So when you import, you can just do from collections, right? This is what I prefer to use. And this is much better actually. From collections, let's import what you need. Import counter, right? Then comma default date, right? If you do this way, like you don't have to write the full name, right? You can just write default date and then just like that for you. Does that make sense to everyone? Is everyone comfortable now how we use default date and counter? But when writing your code now, please be using counter and default date, right? The only case I'll tell you to use counter is assuming the interviewer asks you, tells you to solve this question. Count how many characters are in a string. And then you just write one line of code for them. Return, counter, counter of S. Like, you don't just do this. Like, the interview will end in like 30 seconds, right? Instead, you can be like, so there are a couple of ways I think I can go about this. I can use Python's counter, which is in the collections module. You're like, oh, this guy learns, right? I'm like, but that is kind of a bit too straightforward, so we can do it manually. Then write the manual code, right? But show off, right? You have to show off. Like me, show off what you know. Of course, it can be like, but if it's just a tiny, sometimes it can be like a tiny portion of your code, like group anagrams or something, right? It can be a tiny portion of your code. That one, save yourself time, save yourself that extra 2 minutes by using a counter, and then on and off you go, right? So counter and default data are things we're very comfortable with now. And let's go to deletion. I'm going to talk on deletion, then we go through the time and space complexities for what do you call it, for the hash tables or dictionaries. Okay, next, deletion. To delete from a dictionary, we can delete from a dictionary, right? You have a dictionary, you can be like, hey, I want to delete this E is 2 here. It's very simple. To delete, just use the del keyword, the delete keyword, right? Then the name of the dictionary, then the key, right? This is how you delete from it. So if you delete, this is how you remove the entries from it. You come across questions where you have to delete from there, especially questions that involve like sliding window. Like maybe you are tracking how many items are, are in a set. Maybe you're doing this operation, right? Maybe you're doing the same operation. Maybe you're doing the same operation you see here, but you're doing it for a particular window, right? So that means that the moment you slide past that window, you have to remove some of the entries that are in the past, right? In that case, you have to delete from them. So just know, delete, this is how you delete from a dictionary. Very important to know. Now let's go through section. And section is very important. And I also mentioned section again. I think we did section also for arrays and lists last week. But there's something I forgot to say last week. That is the in keyword.
I have a question.
Yes, go for it.
You talked about if we want to update something and it's not inside, we can use the get function to sort of update something, like if it's not found. But let's say we are going to delete something and it is not inside the hashing up.
What will happen?
So, yeah, what would happen?
That's a good question. You want to delete and it's not in there. What will happen? Anybody has an idea? I beg, I'm not going to answer this question. Anybody has an idea? So we are like, I'm going to delete and it's not there.
I think it's still going to throw key not found or something.
Okay, yeah. So you can also try to see, right? Because like once you try to access, right, like the accessing itself is like, like the accessing itself can lead to an issue, right? Because if delete works like this, then it first has to get it first and then delete it, right? But confirm to see. And if it's getting and it's not there, it's like, sorry, key not found, right? So check that to see. You can also just, after that, you get to the coding session and we will also prove it, right? Okay. Are we good to go? Good to go?
Yes.
Nobody go mind me.
Yeah.
So let's go through the section. Start on the in keyword, right? In, in. One of the cool things in Python too. And what's not seen in before? In Python code before. If K in this, if we've even seen it here, right? In, right? In. So in simply means in. That's all it means, right? Like you can just be like, it depends on list two, right? Like if two in this, right? In 2, 3, 4. I see people writing code and ask them, what's the time complexity of this code? They're like constant time. Because they think in is constant time. I beg, in is never constant time. In itself is not like some super magic thing. No. In simply means, hey, are you in? Right? So the time complexity of this line depends on what you're searching inside. If I'm searching inside a list using in, what's the time complexity? Anyone? Anyone?
It's linear
Linear.
or then
It's linear, right? It's
depends.
linear. Never forget it. It looks very innocent and very cool and very cute, but it's not constant time. If you do two in some list, in will come and you'll be like, okay, are you two? No. Are you two? No. Sorry, the first one is 2, but let's assume it's 12. Like, are you two? Are you two? It has to check every single thing. So this statement is linear time. In is cute, doesn't make it constant time. Okay. But if we do it for a dictionary, if C in map, then it becomes constant time. Why? Because its time complexity is dependent on what it's going to search through. For a dictionary, or for the resources you went through, which we sent, you know how the timing works, right? And everything. Okay. Does that make sense to everyone? The time complexity of in, like when you use in, statements like this, right? So section, you can
Yeah, I
search
have a
using,
question though.
yeah, go on.
Yeah, so for the first one, where you do the in on a list or an array, why doesn't
Yeah.
he use a binary search under the hood?
No,
Just
but
like
then,
curious.
but then assuming this can only use binary search if it's sorted, right? Oh, is it my example that is tricking you? Like, what if this is 12? You can't use binary search anymore, right?
Okay,
You can
yeah,
only
it makes sense.
use binary search if the input is sorted, right? But lists have no guarantee, right? If I tell you sorted list, even if you sorted list, in cannot still what all in needs to know is I'm searching for something, right? In is like a very dummy thing, right? So whether it's sorted or not, in will still do the generic thing, unless you have twisted things under the hood, right? Which you can do with in because it's generic, right? Okay. So next thing I want to also touch about is the time complexity of. So before also look at searching, you can search using in, right? Inside it can be like if this in this and so on and so forth, right? Look at the time complexity and all. So the time people always say the time complexity of dictionaries are constant time. Well, to some extent, that is true. Depends on the implementation. But in your Python code and everything, it's constant for sure because of how things work. But under the hood, it's actually not constant time because of the collisions I mentioned, right? You can get collisions when I'm searching something. So many implementations of dictionaries have the time complexity to be logarithmic time, log n, because some use balanced binary search trees. So some of the, this is usually for the some of the C++ people or some of this who use like, in C++, right? If you do like an unordered, so we have 2 types of hash maps. You have Python also has it, by the way. And it's so cool. My God, I had this interview and the interviewer, so the second round was a meeting with one of the very big engineers. And then he gave me this question, and then it was pretty straightforward. It was like a discussion like we're doing now. It was like, so what is the time complexity of this? I was like, we could use a dictionary and everything. I was like, okay, so what's the time complexity? I was like, it's constant time. He's like, are you sure about that? And he's like, I think it's logarithmic time. Then guess what? The week before, a couple of days, or a week or so before the interview, I come across Python's ordered dict, right? Ordered dict. So I think this is what he was thinking of, right? Ordered dict. So in C++, it's called ordered map, right? Now, this one, searching in it is logarithmic time, log n, right? But this one is not, right? So I think he was thinking of on the ordered map and everything. And I was like, oh, if I use ordered dicts or something, then it's going to be logarithmic time and everything, because that one, they put in enough effort under the hood to actually, kind of balance it and make everything, so that one is going to be logarithmic time, right? So whenever you're in this conversation, know that, like, don't be so rigid and be like, there's always constant time, right? You have to understand it. And even the fact that we say dictionaries are constant time, you have to know why it is constant time, right? You realize it's actually not necessarily constant time. It's constant time if, as you saw, we had the bucket here, right? Like if every time you're putting something into the bucket, it was straight away, like you hash it, and all you have to do is just put it in. Hash, put it in. If you want to get it, it's simple. Just come and get it, right? Then this makes it constant time. But sometimes as you're putting in, right, you come across collisions, right? Something is already there. So you begin to form a chain, right? You begin to form a chain. So let's assume this guy is what you're looking for, right? This guy is what you're looking for. So you hash it here, like, oh, come to bucket 2 here. So you come to bucket 2 here, but you come in bucket 2, there are already items in bucket 2. So now you have to go up and search across this chain to find the thing you have. So it was constant to locate the bucket, but going up the bucket to find item 2 is work that is being done, right? But what we do is that we're like, oh, this doesn't happen so often, and it's just some part of the operation. So what we do is that we distribute this effort across the whole operation and still say it is constant time. Does that make sense to everyone? What we say hash pumps are constant, or dictionaries are constant time. Like, it's not like under the hood, it's not like pack constant. Yeah. It's more like we distribute what we call amortization, right? We distribute some of the effort across it, and you're like, oh, it's approximately constant time. Like, you'll be like, I'm not searching the whole bucket to find it. No, I first jumped to this place, then I just went through some short chain, right, to locate it. That is why your hash function has to be good. But if your hash function is bad, right, properties of hash function, the hash function you use always has to be good. The hash function is bad. If you don't take care, even though there's a long bucket, you have this bucket to be very long. Somebody, if hash function, like, can put everything in one bucket, right? That one, it becomes like a linear search, right? Because like you're basically wasting the other ones. But a good hash function will distribute everything almost uniformly, right? A good hash function will distribute everything uniformly. Does that make sense to everyone? So the time complexity. Go on.
Yes, what about the ordered dict makes it like
ordered dict. So what ordered dict does is that it stores the thing in the form of a binary search tree. So this is how ordered dicts work. So if you order it, right? So ordered dicts means that, and ordered dicts are very powerful, actually. I'll show you how powerful they can be. So realize that if you create your defaults, like, don't think C+ or anything. Follow me, I'm still teaching Python. What I'm doing is Python. Ordered dicts is Python, actually. It's Python. Yeah. What's the name of the I think I think Python calls it sorted. It's from sorted maps or something. I'll show you the module, actually. So this is how it works. So let's assume you're putting, everybody follow me here. You're putting 2, let's say 2, 2, right? So these are key, this is our value. This is what you want your map to look like, 4, 4. Let's say 1, 1. This you want to put this, right? So what the other dicts does is that it will come and then it should be like, okay, 2, 2. So to create a binary search tree. You don't know binary search tree, follow me, you don't get confused. It's very simple, right? So to be like 2, 2. So to create a node here, then to be like 2, 2, right? Then so it's done this insertion. 4, 4. So for a binary search tree, the bigger one goes to the right. So to create 4, 4 here. Please follow me. If you don't, we'll do trees later, but we are not there. But just follow me, just answering this one. And then 1, 1. So 1 to come here. It's always start from the root to be like, oh, 1 is less than you. So 1 should go here, right? 1, 1. So for that one, whenever you try to do map index, say 1, right? What it does is that map index 1, it comes to the root node. Then now it's like, oh, 1 is less than 2. So basically it's traveling, right? Like it's making the travel. So like it will travel and travel till it finds the 1, right? And the length of the height of this tree is going to be log n. The height of this tree is going to be approximately log n. So it will have to travel like log n nodes. Like it has to come here, come here, come here, come here before it finds what you're looking for. So that one, the session becomes logarithmic time, right? It uses a balanced binary search tree under the hood. It doesn't use this thing we're talking about here, right? For the sorted ones. It uses some kind of sorted data structure, which is usually a binary search tree under the hood. We'll touch more on this when we get there. So that's why that one is log n, right? So, and they actually use this for this. They're actually very important uses for this. This is some of the important uses for that. So the sorted data, one cool thing about them is that when it sorts it, right, it keeps some specific, I think there's actually a question I've solved before, which required this. Like, so you see the regular, I'll solve a question we get there, but I just wanted to know that in Python, you can have a dictionary sorted. I'll show you the library, the documentation for that later. So time complexity of dictionaries are generally constant time. In Python, just put that in your head. It's constant, it's constant. If you come across a case when an integer tells you that it can be logarithmic, you can honestly be like, oh, if it is sorted, right, under the hood, then yes, it could be logarithmic because it's just a binary search tree, which we'll talk about later. But I just want you to have that thing in mind. Does everybody understand? Does it make sense to everyone? I don't want to bring everything inside right now.
Yeah.
People don't get confused or anything like that, right? So again, we've explained what this in guy does. Please, in is not constant time, or it depends on what it is operating on. On a dictionary, it's constant, right? And I've also explained why when we say a dictionary is constant, it should have been in the videos, right? I hope the volunteers who found the videos was got something good like that in the videos. So that is that for that. Okay, so that's what I want to talk about with dictionaries. The last one to talk about in dictionaries is this. Please follow me carefully here. Those who join the coding room, last Sunday, we mentioned this, right? Let's assume they want you to, I'm still on that counting question. No. Let's assume you have a string. Please listen to this part. It's very important. It's going to help you get the offer. Okay, look, let's say you have give me your favorite English word. Anyone. Favorite English word.
Mouse.
Mouse. Hey, you said mouse. This?
Yeah.
Hey, that's thank you. Okay, mouse, favorite English word. They want to count the number of occurrence of every character in it, right? So mouse, so M occurs one time, right? O occurs one time, right? Please follow me carefully. U occurs one time, right? S occurs one time. Then E occurs one time, right? Now, so this is right? And I can be like, oh, give me maybe how many times O occurs or something, right? So this is fine, right? But it is not always that you have to use a hash map. Hash map is kind of like the default thing people use when you hear something like count something. But look, listen to me carefully. Whenever you want to count something, right? And then the thing you are going to count is bounded. It's bounded. So for instance, they tell you that the input S is going to be composed of English lowercase alphabets. Do you agree this is bounded, right? There can be only how many English alphabets are there? Anybody?
26.
26, right? This is bounded. It's going to be 26. Do you agree this is bounded? It's going to be 26. Like there's no way if I give you whatever word, whatever S is, whatever value of S I give you, it's always going to compose of 26 unique characters. Do you agree? It will always be.
Yes.
Right? If it's not A, it is B. If it's not B, it is Q. Right? Now, if I want to count this, I don't need to go all the way to create a hash map to count this. I don't need to do that. Right? I don't need to do that. I can simply use what we call a list, as we saw last week, right? Can use a list, create a list of 26 entries. Can just create a list of 26 entries like this. And then initialize everything to 0, right? So you know the first one corresponds to A, B, C, D, E, F, G, H, I. Does everybody see it? So now, if only let's say if I see A, let's say the word is apple. If I see A, I just need to know that I have to go to the first entry and increment this by 1. Does everybody agree to what I'm doing? Does everybody see what I'm doing? Am I on
Yes.
the
Yeah.
So now the question then becomes, how do I go from A? How do I go from this A, right? How do I go from this A to this index 0, right? How do I go from this A to this place? That's a question, right? We ask ourselves now. Well, Python again, superpower. Actually, every language does this. So Python will be like, oh, to get A, you can just do alt. If you do alt of a certain character, it's going to give you the ASCII value of it, right? So let's assume the character is A. So alt of A, I think it's 97. It's going to give you 97, right? But this is 97. I just want it to be index 0, right? This is index 0, index 1, index 2, index 3. I just want it to be this, right? I'm like, sorry, I don't want this. So if someone knows 97, will be like, okay, then it should be the odd of the character minus 97. But I don't want to keep 97 in my head. That is too much, right? So be like, okay, it's simple. Just do odd of the character minus odd of A, right? So all you need to know is the odd thing. So so if the character is B, this becomes odd. Please follow me. It's not long. It's not long. I'm just breaking it down. That's why you mean lengthy. So this becomes odd of B minus odd of A, right? Odd of A. So if odd of B is 98, odd of A is 97, and end up getting 1, which is index 1, right? Like just come to index 1 and increment B by 1. Do you all see it here? So we're able to do with a list, right? Or with an array because it's bounded, right? Like it's bounded. We know it's going to be 26 characters. So we even need to bother ourselves with a map, right? Now, those of you who solve group anagrams question on Sunday, you know, I explain this into you, and this makes the time complexity linear time, right? It makes it very quick, right? Because some of you ended up creating this, then you come and do sorted, that's n log n, and blah, 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 blah. You could have just done this, cast to a tuple, and that's linear time, right? So if it's bounded, just do this. There's another question we come across where sometimes, let me show you that one last one before we go. I think it's really cool though. Are we all here? Can we go? Can we go?
Yes.
Let me show you that one. Okay, look at this. Let's assume, right? Just assume, right? But they want to find, and it's actually a very popular question, which you should know. Let's assume that we want to find, please follow me carefully. This question is very important. Is everybody here? Like twist your brain, like be like I'm ready, right?
Yes.
Let's assume we want to find the top, like the top 2 most frequent elements. Somebody's like, this is a lot of English. This is what I mean, right? So I'm going to give you a list. 1, 2, 1, 3, 4, 2, 1, right? So I'm like, hey, I want you to give me the top 2 most frequent elements. So for instance, 1 occurs how many times? Anyone? 1 occurs how many times? Somebody help me. 1 occurs how many times?
3 times.
1 occurs how many times? 3, right? You can put in the chat. 1 occurs 3 times. Do you agree? 2 occurs how many times?
2.
2. Okay. 3 occurs how many times?
1.
Okay. Let me make it a bit scary. Let's make, instead of 3, I don't want it to be like, I don't want it to look like it's consecutive. Let's make this, let's say 8, and let's say this is 12. Okay. So this is 8, and this is 12. Okay. So do you agree? So if I tell you to give me the top 2 most frequent elements, what's the answer? Anybody can help me. I want to see if people understand the question. What's the answer?
1 and 2.
1 and 2. Do you agree?
Yes.
Do you agree?
Yeah.
Do you agree?
Yes.
Okay, good stuff, good stuff. So now, so this one way we can solve the question, right? We can just construct this dictionary, right? Then you're like, but then, see, the dictionary, oh, note, by the way, for a dictionary, oh, I almost forgot. For a dictionary, I beg, you can only access the keys directly. You cannot be like map, like you don't have access to this. This is not what we hashed, right? We hashed the keys. But here you realize that you need this to make the operation, right? Like you need this to choose this. Do you see? A dictionary, you use the key to find the value. You don't use the value to find the key. Does that make sense what I'm saying? Hello?
Yeah.
Yes.
Yes.
But realize this question, you actually need to use the value to find the key, right? So then this is complicated, right? So then you now have to do something. But let me show you one thing. That if you have a dictionary called map, if you want to find the list of the keys, you can just do map.keys. Map.keys will return to you an iterable. You can say a list of the keys, right? So if I do map.keys, this will return to me like 1, 2, 8, 12. By the way, it's very useful. It's very useful. If we do map dot, trust me, this thing is so useful. It's so useful. You have to know it. If I do map dot values, that return to me all the values, also as an iterable, like a list. You can loop through, you can do everything on 3, 2, 1, 1. If I also want to get the pairs, right, and do map, anybody to help me, map dot what?
Items.
Good, map dot items, right? And that will give you like 1, 3, 2, 2, 8, 1. And trust me, this is very useful. Like this thing, I wish I could do emphasize, like it's so useful. Like these things become life-saving. Like sometimes you're looping through it, right? So because like this, you can just do for K, V in map.items, right? Those of you like using, last time I said what was using enumerate. Those people, this is what they do. Like, right, this goes, right? So yeah, then you be like, okay, let me sort it. Let me sort on this. We'll do sorting like next week. Sorting, passing. I think yesterday, those who joined the coding room, we talked about lambda functions, right? We'll apply it to sorting later. Okay. So then, this is a very, so like, this is complicated, right? Because you now have to get this, then sort it, then use it. Like, it's complicated. But then, let's see what we can do here, right? So using a dictionary, this question becomes complicated, right? But let's see if we can still use a list to solve it. I'm just telling you that a dictionary is not always the way out, as people always think it is. Sometimes there are things that make other data structures much better, like a list, right? Now, it's shown to you one way we can do that, like if the input is bounded, right? I'm sure give you another case. So here, there's also some form of bound here, right? There's also some, follow me carefully. Here, what was the bound? What was the bound we used? What was the reason we used? This was the reason, right? We said that the input is going to be composed of English lowercase characters, right? And we know there are only 26 of them, right? So we are like, hey, this map is going to be at most 26 entries, right? It's the same as just having 26, and they're also ordered. We know A is index 0, this is index 1, and so on, right? There's already some form of structure already created, right? So let's apply the same thing to this question. Can everybody see a structure that is created here? There's some structure here. Can anybody help me with that? It's a structure here. Okay, let me show you the structure. Structure number 1. What is the maximum value we can get here? What's the maximum value we can get here? So note, this is the number itself. The number, that is the number inside here. That's the value. Let's call it number. So not be confused. This is the number. And this is the frequency. The value is the frequency. What is the maximum frequency you can find here? What the maximum frequency? What's the maximum frequency?
7.
3.
It's actually not 3. I mean, based on this
7.
question, it's 7, right? because you can get a number that the highest occurring number can have a frequency of like 7. There's 7. 1, 2, 3, 4, 5, 6, 7, right? Like the number can occur at most 7 times. The number that is assuming that everything was that number 1, 1, 1, 1, 1, 1. Do you agree?
Oh yeah, yeah.
That's everybody agree.
Oh, yeah.
That the
Yeah.
frequency is 7.
Yes.
Which means, and that means that again, that simply means that, right? If I have a list of 7 slots, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, right? I can still use this list to behave as a map, as a dictionary. I can still do that. So now the indices, right? The indices are going to be like the frequency, right? So this is like index 0, this is index 1, this is index 2, this is index 3, this is index 4, index 5, this is index 6. Let's add index 7. So I'm just shifting it. So like, I'm like, nothing will occur 0 times. I can just put 0 here. Or you can also shift it forward. Does that make sense? Like what I just did here. Like I'm using the indices as a frequency, how many times the number occurs, right? So I'm like, indices is Python lists are 0 indexed, right? So I'm like, I'm just going to use that as a dummy thing. I'll never touch this guy, right? But like, if you're in there one time, if you occur one time, I'll put you here. If you occur 2 times, I'll put you here. If you occur 3 times, I'll put you here. 4 times, I'll put you here. 5 times, I'll put you here. I'll put you here. Does that make sense? What I just did here?
Yes.
Yeah.
Okay, please follow me carefully. So now if I'm going through my list, I'm like 1. I'm like, I've seen 1. Oh, I'm like, oh, this. So let's say I've created this guy, right? I've created this guy, this map here, created this map here. Like, oh, now looking at this map, I'm like, oh, 1 occurs 3 times, right? So I come here, now look for index 3, then I'll put 1 here. I'm like, 2 occurs 2 times. I'll come and put 2 here. 3, I'm like, oh, 8 occurs 1 time, right? So note the frequency is the index, right? 1 time. 1 time. So I'll come to the 1 time. This is the box 1 time. I'll put 8 here. 12 occur 1 time. I'll put the 12 here too. 12 here too, like this. So now, what is the question asking us to find? The top 2 frequent elements, right? Now, the top 2 frequent elements, if it's 7, if anybody is in 7, they occur more than the thing here, which 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 occur more than the thing here. Do you agree that if you occur at the later end, you occur more times? Because the indexes are basically the frequency. Does that make sense to everyone?
Yes.
Yeah.
Yeah.
Does that really make sense to everyone? So now, if I want to find, so after I've created my dictionary, right? The dictionary helped me to get some halfway. Like, I'm like, dictionary, thank you for your hard work. Thank you for your service. Then now I continue to use the list, right? Because if I try to now be like, let me create a tuple and then I will sort it based on the value, you're not finished today. But we know there's some kind of boundary. And look, we're still exploring the concept of boundaries, right? They'll say a bound. The bound is, well, the value can be at most the number of, and at most the length of the input, the length of nums, right? Or 1, right? We're like, oh, then if the length of nums is not going so big, I can just create a list like that, right? And this one is going to be linear time. I'm creating this list is going to be linear time, O of n. If you try to go and sort and do the sorting stuff, that's going to be n log n, right? And this is much, much better, right? So if I want to find the top 2 elements, I just need to look from the back. All these are 0 because there was no item that occurred. So I just need to look from the back. So then I see 1, because that's at index 3. I'll be like, okay, 1, I saw 1 first. Then I continue looking. I see 2 first. So this is how you solve the question, top k frequent elements. This is basically how you solve the question. So you just need to look coming from back and just till you find k elements. So this is 1. So if k is 3, you get here the 2 elements, just choose any of them. You can choose the 8. And then you're done. Does that make sense? Does that make sense to everyone?
Yes.
So I'll show you a case where you don't necessarily need a map, and a dictionary, in the case where a dictionary brings you halfway, and then like you are done. Like you don't need to apply sorting or anything. And the list can still help you. This is why we did list first, right? And that makes sense. Okay. We are good on dictionaries. We have to go to the next topic. Does that make sense to everyone? Makes sense. Are we good to go?
Yeah.
Okay. I'm giving you 1 minute. 1 minute break. Stretch your body, get water, or anything you want. If you have a question, this is the time to ask your questions.
Yes, so the 8 and 12, is it gonna be another list?
Yeah, exactly right. It's going to be a list. So this is called buckets. So actually, these are going to be lists. They're going to be lists inside. Yeah. Have you solved the question top k frequent elements, right?
Yeah.
Yeah, this is the best algorithm to use, right? It's much more efficient. Yeah, so inside is actually a list. These are lists, this is also a list. But you can actually should I show you something very cool? I'll show you when we do the coding section. Let's do the coding section for dictionaries now. Okay. Break is over. 1 minute is over. Okay, let me show you. Cool stuff. Let me share my screen. Okay, cool stuff. people are most excited about this part because you get to prove that everything we discuss is not wrong. I mean, like, not like wrong, but like wrong. Oh, you don't want to expand it. Okay, look at this. Can you see my screen?
Yes.
Okay, good stuff. Good stuff. Okay, what do you want to show first? Let me see. Let's see. Back up. Oh, let's first do the deletion thing, right? So let's say we create our dictionary. Let's call it count. And let's say now we have like 1,2, right? Let's say we want to delete. Oops, what have I done here? This is a set. Okay, after dictionary, we're doing sets. Please remind me. Set is very pop. We'll be done right now because we understand dictionary. Set will be like, it will be like, trust me. Okay, so delete will be like count. Then we pass the key to it, right? So let's first try this, and now let's print. Please follow me. If you don't get tired, don't get weary. Don't get weary. Don't get tired. We'll be done so soon. Okay, so execute code. Okay, so at first it was 1, 2, right? And after we deleted, right? After we deleted, it became empty. Can we all see it? Do you all agree?
Yes.
Everybody can see it, right? Like, okay. Please,
Yeah.
does everybody see it? Okay, good. Now let's see. Then the brother asks, what if we delete something that is not in? So let's say we are deleting 5, right? Execute code and see key error, right? There's a key error. Can we all see the error here? Because it tries to get count of 5 and 5 does not exist. Therefore, that gives us a key error. Can we all see? So we know if you're trying to delete it, it leads to a key error, right? If you're deleting one, it's not in. Okay. I don't know if this guy has collections though. Let's create our account again. Let's do with counter. Let's do counter first. I want to show you something cool about counters. I don't think this one has counter, but let's try. Let's pass S to it. Let's make our S a string. Amane. Cool. Okay. Let's try. And let's print S. I don't know. Oh, it has it. Okay. Now, okay, it has. So now let's print S and count. Let's print both of them. Okay, so you can see count here. Can you see what count is? It basically did that job, right? Like using the for loop, going through counting everything. Can you see here? A occurs twice, N occurs 2, right? And count, and this counter objects, right? You can see counter here, but don't just think of it as a regular dictionary, right? It's because it's counter objects. But look, it's basically the same thing, right? You can basically treat it as a dictionary. Like you can loop through it. Can be like print count.keys, like count.keys, and just like, and we know what map.keys does, right? Like keys, and that gives you like, the same thing, right? It gives you the dictionary keys, right? A, M, just the same thing, like just treat it just like dictionary. But there's another cool thing though. Look at the other cool thing. Look at the other, you've seen this question before. If one string is a substring of another, if one string was derived from another one, right? So for instance, what I mean is this. Let's say you have two strings, strings 1. Let's say string 1 is, let's say, ama, and string 2, S2 is am, right? And want to check if first one was derived from the second one, right? So let's create S1 count, right? So we have counted S1, and then you have created S2 count, right? And that's also counter of S2, right? And now look at something. Let's print both of them, and I want to show you something cool. Now, it means you must know it too, by the way. Like you have to know it to save your life, it to save your time. Now let's print S1 count. You can actually subtract them minus S2 count. Look, I'm going to subtract them. Look at something here. So now let's execute code. And you can see, look, can you see S1 count? A occurs twice, M occurs once, right? So now if I subtract them, note, if they were the same, right? Like if they were the same, the dictionary would have been empty. But no, it's not empty. That means it's like, hey, the first guy has a surplus, right? The first guy has a surplus remaining, right? So, you can apply this to many questions actually. And it's like really cool. So I really like counter. It's a cool thing. Now let me show you the sorted dict. Okay. I was looking for sorted containers. Yeah, sorted containers, really cool. Okay, look at this. Sorted says sorted dict. So this is what sorted dict does. We don't have money today. Okay. So this was sorted. So there's also sorted lists and all these things, but they implement these number things in under the hood. So sorted sets, I think you should just go look at this on your own. So this is the sorted dict we have. Give me a second. So it is immutable, as you can see here. That maintains the keys in sorted order, right? So it's just like this. And they didn't even add the time. So I just want to show you there's something like this. And it's from sorted containers, right? So just use from sorted containers, import sorted dict, right? And you can have your dictionaries in sorted order. The questions why this thing becomes very useful, actually. I've come across one before. I think I use it in place of, I think, a heap or a try. I think it was a piece of a try, something, forgotten.
So
But
does that mean like hash maps are not like ordered
they're
and
not
like
ordered.
sorted dicts are ordered?
Yeah, hash maps are not ordered. Like when you create a dictionary like this, like there's no ordering. Like, right? Like there's no ordering. It puts it in, like the dictionary bring the order you put it in. It doesn't order it. But that sorted container, like if you put it into order based on the keys. So let's do first you put, let's say M in. If you bring B in, it will move the B here. It's coming to put the B second, right? Like it will rearrange it in some way. And that rearranging is time effective, right? It's cost. It's costly. That's why it becomes logarithmic time. Because at each point, it has to like rebalance it, right? It has to like rebalance itself because a balanced binary search tree. That's what makes it logarithmic time. Yeah. And that is basically the default in many programming languages. Like if you do like in C++, if you do like on ordered dicts, if you do ordered dicts, like if you want the Python generic one, it's on ordered dicts. But if you want the sorted container one, that's what you call the ordered, what am I doing? Ordered dicts, so on and so forth. Okay. So what other thing do I have to demo? Then that's pretty much it. Let's go to the next topic, sake of time. Are we good to go to the next one? Set is like path. Because they've understood hash maps, dictionaries, sets are like pop, we are there. Okay, let's do it quickly. Please don't get tired. Don't grow tired. Don't grow weary. Okay, please, can you end the recording and restart a new recording? I want to separate the set one.